Okay, here we go with curve sketching 2. This we now introduce the asymptotes to the sketches we've done before. So this is going to be 2 short little videos on that with just a couple of questions to practice for yourself. We have horizontal asymptotes, vertical asymptotes, and we're going to introduce other asymptotes in the next lesson. Now notice here that the vertical asymptotes occur as the limit of f of x tends to infinity. But the horizontal asymptotes are actually, no, those are still vertical. The horizontal asymptotes are actually the limit as x tends to infinity. So for the horizontal, we want the limit as x tends to infinity or negative infinity. But the vertical, we want the limit to tend to infinity. So let's have a look at a couple of them. Limit of f of x as x tends to infinity equals a means that y equals a is an asymptote. So if you try to find a horizontal asymptote, y equals asymptote, just find the limit as x tends to infinity, which you can now do using L'Hopital's rule. For example, here, if f of x equals x over x plus 1, and I want to know the horizontal asymptotes, because now you'll notice we no longer have a constant over an x, we now have x's over x's. I find the limit of x over x plus 1 as x tends to infinity. Now, if we substitute, we get infinity over infinity. So that is indeterminate, you'll remember from the indeterminate limits. And when it's indeterminate, infinity over infinity, or naught over naught, you can use L'Hopital's rule. And L'Hopital's rule says that the limit as x tends to infinity of f of x over g of x is equal to the limit as x tends to infinity of their derivatives over one another. Very useful. So here we go here. We have the derivative of x is 1. The derivative of x plus 1 is 1. So now we know that the limit of a constant is just the constant. So therefore y equals 1 is the horizontal asymptote. The limit of f of x as x tends to a being equal to infinity means that x equals a is an asymptote, and we've already handled those all the way along the line. So we use the limit as x tends to a to find the vertical asymptote. The values of x which will result in division by 0. So summarizing, horizontal, the limit of f of x as x tends to infinity, and the vertical, x equals a, where the limit as x tends to a of f of x equals infinity. Note, the limit of f of x as x tends to negative infinity should also be used to find the horizontal asymptote. Because have a look, this one's going that way. And it's going that way. So you'll find that the y equals 1 is the asymptote. And as this function tends to infinity going that way, it'll tend to 1. And as x tends to infinity going that way, it'll also tend to 1. So the left limit is equal to the right limit, what we are saying. So let's just have a look at finding the horizontal and vertical asymptotes. Horizontal, they've actually become quite easy then. Because remember, horizontal asymptote means I'm going to find the limit as x tends to infinity. So we're going to find the limit as x tends to infinity of 2x minus 1 over x plus 5. And that's equal to infinity over infinity, which is indeterminate. So we can use L'Hopital's rule, which means I can say y equals the limit of the derivative of the top, which is 2, over the derivative of the bottom, which is 1. And that's become a constant, and the limit of any constant is always the constant. So therefore y equals 2. To go this way, we say, well, what does x tends towards for the limit to equal infinity? Well, we know that you've done it already in just class maths, that x equals negative 5. X cannot be equal to negative 5. So that's the limit, x tending to negative 5. There we are. X tending to negative 5. So therefore, there are our horizontal and vertical asymptotes. Y equals 2, x equals negative 5. This one here. All right, we're going to do the same thing. Horizontal, limit as x tends to infinity. So there, x is tending to infinity. We're going to take that. That's infinity over infinity. If I substitute infinity in for x, I'm going to get infinity top and bottom. So therefore, I could say it's equal to the limit as x tends to infinity of derivative over derivative, because it's indeterminate. And we end up with that, 2x minus 2 over 2x. And of course, that's still indeterminate. So I can go a stage further. I can differentiate again. So we end up with a limit of 2 over 2 as x tends to infinity. It's now constant, so that's equal to 1. And therefore y equals 1. Now we're going to look for the ones that give us undefined in effect. But I want to know what x must it approach to go to infinity. Well, we factorize that because now we can see the values of x that are going to make the denominator 0. There we are. X cannot be equal to 1 or negative 1, so there are your asymptotes. Right, 3x minus 5 over x squared plus 16. Why don't you pause and try it yourself, this one. I hope you paused. Y equals, right, I'm finding horizontal, so I'm going to find the limit of f of x as x tends to infinity. We want to see how far left and right we go where we hit the asymptote. So therefore, I'm going to find the limit of that as x tends to infinity. There we are. And if you have a look, it's infinity over infinity. If I put infinity in the top and infinity in the bottom, I'm going to get infinity in both. So it is indeterminate, so I can use L'Hopital's rule. So I'm going to have limit as x tends to infinity again, and I'm going to put derivative over derivative. Now, hopefully you'll remember that any constant over x tends to naught as x tends to infinity. So in fact, here we go. You could use L'Hopital's rule. No, you can't use L'Hopital's rule because it's not indeterminate any longer. We don't have infinity over infinity. We have a constant over infinity, which tends to 0. There we are. Y tends to 0. No vertical asymptote. Have a look. You cannot make that 0, so you cannot make this tend to infinity. This one you've got to be careful of. There's the warning. Because hopefully you recognize that you can factorize and something's going to happen there. Now have a look what we have. We have x minus 4 over x minus 4. So those can cancel, giving us just x plus 1. So this is almost the same as y equals x plus 1. But even though we've cancelled out the x minus 4s, x can't be equal to 4. So there are no asymptotes here with this one, even though it looks as if there might be. We're going to have the graph y equals x plus 1, straight line graph, but we cannot have x equal to 4. So no asymptotes, and there's my graph. Y equals x plus 1, but notice we're excluding x equals 4. Let's sketch a curve. So we're going to have to go the whole way. We're finding axis intercepts. We look to see if there's a turning point, everything. So let's find the y-intercept. Y-intercept when x is 0, and so negative 1. And there we go onto the graph. X-intercept, we're going to put y as 0. And if you solve that, you're going to end up with x equaling negative 2. Let's have a look at turning points, just to see. Because you're not quite sure, is this a hyperbola? I'm not quite sure, so let's just check on turning points. This is a quotient rule, so therefore I have to say derivative of top times the bottom minus top times derivative of the bottom. I've just put these the other way around for neatness. Over the denominator squared. So derivative times that minus derivative times that all over that squared. That's our quotient rule. And it simplifies to that, and that can't be 0. If you have a look, this can't be 0, the whole thing, because we don't have an x on the top. If you don't have an x in the denominator, you cannot get a 0 out of the fraction. So therefore no stationary points. Let's have a look at the asymptotes. I'm going to find the horizontal and the vertical. So the limit of x, as x tends to 2 of x plus 2 over x minus 2 equals infinity, we can easily recognize that, which means there's our vertical asymptote, x equals 2. Now I need to find that limit as x tends to infinity for the horizontal. That there is indeterminate, so I can use L'Hopital's rule, derivative over derivative, and so it's the limit of 1 over 1. Constant, so therefore that's it. And there is your asymptote. So now have a look. We have crossing there and there, and asymptotic to here, asymptotic to here. You might want to check. You could check by substitution. For example, if you put in a value of 3, what are you going to get? Well, if I put 3 plus 2 is 5, 3 minus 2 is 1, 3, 5, it's going to be up here. Oh, so we still have a hyperbola, but just off axis for both of them. At the stage, let's take it back to where it was. At the stage, that's the end of this little video. And what you must do now is you must go along and do the exercises. That's curve sketching exercises, curve sketching 2 exercises. As indicated in your lesson notes. I've just done a check. It's numbers 1 and 2 of that set of exercises.